Assalamu alaikum students. This is Dr. Haseeb. Hope you are doing well. Today we are going to discuss a very important topic of sensory nervous system, that is synapse and properties of synapse. So before going on to the properties of synapse, we will finish the remaining part of the previous lecture, and we will touch briefly on properties of neurotransmitters and how do they differ from neuropeptides. So by the end of today's session, inshallah, you will be able to differentiate neurotransmitters from neuropeptides, and this will be followed by the properties of synapses. We have already discussed the two types of synapses, the physiological types of synapses, electrical versus chemical, and we will discuss few of the important properties of synapses. There are many properties. We will try to cover as many as possible, focusing on the relevant and important properties as far as your professional examination is concerned. So we have frequently used this term neurotransmitters. You all know what are neurotransmitters. Uh, Another interchangeable term is neuropeptide. Although these two terms are synonymously used, but there are slight differences between the two. As far as the neurotransmitters are concerned, they are also known as small acting, rapidly acting neurotransmitters or small molecular substances, whereas the neuropeptides, they are also known as the slowly acting transmitters. The primary difference between the two is the site of synthesis. As far as the classical neurotransmitters are concerned, the site of synthesis is within the cytosol of the presynaptic neuron. So almost all the rapidly acting neurotransmitters are synthesized within the cytosol of the presynaptic neuron, whereas the site of synthesis for the slowly acting neuropeptides is the ribosomes and the Golgi apparatus. So as the name indicates, these are slowly acting neuropeptides. The onset of action and the duration of action is relatively slower as we compare it with the fast acting neurotransmitters. And this is the classification given in your textbook. This is the classification for the fast acting neurotransmitters, and we have classified these neurotransmitters into four groups or four classes denoted by the capital Roman numerals. And the most important is the class 1 neurotransmitter, acetylcholine, an excitatory neurotransmitter. Then we have amines in class 2, amino acids in class 3, and nitric oxide has been categorized under class 4 neurotransmitter. Class 2 neurotransmitter, the amine group, it contains the adrenaline and noradrenaline, also known as epinephrine and norepinephrine. Both are very important. Both exhibit excitatory as well as inhibitory effects. Then there is dopamine, another important neurotransmitter, followed by 5-hydroxytryptamine, commonly known as serotonin. Similarly, in amino acid group, class 3, we have two inhibitory neurotransmitters, GABA and glycine, where GABA stands for gamma aminobutyric acid and glycine. So this is the classification for the fast acting neurotransmitters. We have classified these neurotransmitters in four classes. Now here is the complete list for the slow acting neuropeptides. As the name indicates, the onset of action and the duration of action is slow relatively than the neurotransmitters. Hence, we call them as slowly acting neuropeptides. And you can see these neuropeptides, they contain the hormones from the endocrine glands. Then there are substances related to the GI tract. There are substances related to the central nervous system as well. For example, hypothalamic releasing hormones, TRH, LHRH, and somatostatin. Thyrotropin releasing hormone, luteinizing hormone releasing hormone, and somatostatin. The other name for somatostatin is growth hormone, inhibitory hormone, or inhibitory factor. Then there are pituitary hormones, which includes prolactin, thyrotropin, growth hormone, thyrotropin, luteinizing hormone. All these are the anterior pituitary hormones. Plus, we have antidiuretic hormone and oxytocin. These are the posterior pituitary neuropeptides. Other important neurotransmitters, rather neuropeptides, include substance P, gastrin, cholecystokinin, insulin, glucagon. All these neuropeptides are related to the GI tract. Similarly, angiotensin 2 is another neuropeptide which has important role in the renal system. So you can also view the list from Gannon's physiology. Here is the examples of rapidly acting or fast acting small molecule neurotransmitters and slowly acting neuropeptides. So these are the differences between the classical neurotransmitters and the slowly acting neuropeptides. As the name indicates, slowly acting neuropeptides, the onset of action, the duration of action is very slow. Similarly, neurotransmitters, the onset of action and the duration of action is very fast. This is the major difference. Then is the site of synthesis. As we have discussed, the site of synthesis for the neurotransmitters is within the cytosol of the presynaptic terminal. Unlike neurotransmitters, neuropeptides are synthesized not inside the cytosol but inside the endoplasmic reticulum, the Golgi apparatus, and the ribosomes. So this is another important difference between the two. Then is the site of storage. As far as the neurotransmitters are concerned, most of the neurotransmitters are stored inside the synaptic vesicles in the axon terminal. On the other hand, the neuropeptide, the slowly acting neuropeptides, they are stored in the large dense core vesicles inside the axon. So not only the site of storage is different, but sometimes the site of release is different. For example, the site of release is axon terminal for the neurotransmitter, whereas the neuropeptide may sometimes be co-secreted with the neurotransmitter from the same axon terminal. Similarly, the amount of release is variable for the neurotransmitters, and it all depends on the type of synapse, whether the synapse is excitatory in nature or inhibitory in nature. So the amount of neurotransmitter released at these synapse is variable. However, neuropeptides are secreted in much lower concentration as compared to the classical neurotransmitters. So these are the important differences between neurotransmitters which are fast acting, and neuropeptides which are slow acting. So to summarize, neurotransmitters and neuropeptides, although wrongly interchangeable terms, but there are differences between the two. The site of synthesis for neurotransmitter is within the cytosol. The site of synthesis for neuropeptides is inside the ribosomes. Similarly, the site of storage for neurotransmitter is inside the synaptic vesicles, whereas the site of storage for neuropeptides is inside the dense core vesicles. Moreover, the amount of release is variable as far as the neurotransmitters are concerned. However, neuropeptides are released in much lower concentration. So we have classified neurotransmitters, we have classified neuropeptides. Another way of classifying neurotransmitters is on the basis of the effect that is produced by the type of synapse. So whether the type of synapse is excitatory in nature or inhibitory in nature. That is why we can also classify neurotransmitters on the basis of excitatory or inhibitory nature of the synapse. For example, acetylcholine is an excitatory neurotransmitter. Similarly, nitric oxide, glutamate, all are excitatory in nature. The classical inhibitory neurotransmitters include GABA and glycine. These are the classical inhibitory neurotransmitters released in the nervous system: gamma aminobutyric acid and glycine. Other neurotransmitters which exhibit inhibitory properties are dopamine and 5-hydroxytryptamine, that is serotonin. So we can classify neurotransmitters as excitatory versus inhibitory as well. The thing to remember is that some of the neurotransmitters, they do not show entirely excitatory properties or entirely inhibitory properties. Hence, we can classify these neurotransmitters as mixed neurotransmitters. Or you can say the neurotransmitters that can exhibit either excitatory property or inhibitory property. For example, epinephrine and norepinephrine. These two neurotransmitters, they sometimes exhibit excitatory response and sometimes they exhibit inhibitory response. And the type of response exhibited by these neurotransmitters is dependent on the type of receptor that they are going to attach on the postsynaptic membrane. If the type of receptor on the postsynaptic membrane is of excitatory nature, then the receptor response, or the you can say the neurotransmitter response, will be excitatory as well. Similarly, if the type of receptor on the postsynaptic membrane is of inhibitory nature, in that case the type of response produced by the neurotransmitter will be inhibitory as well. For example, epinephrine and norepinephrine both exhibit stimulatory or excitatory response on the cardiovascular system, the heart. In contrast, the same neurotransmitters, they exhibit opposite effect, or you can say inhibitory effect, in the gastrointestinal tract. Although the neurotransmitters are the same, but the type of effect is different. So these neurotransmitters are classified as mixed neurotransmitters. So we have discussed the differences between the neurotransmitters and neuropeptides. Now we will discuss properties of synapses. You all know what are synapses: union between two neurons. Technically speaking, synapse is different from neuromuscular junction. When we use the term neuromuscular junction, this means there is union between a motor nerve fiber and a muscle fiber, that is skeletal muscle. When we use the term synapse, we are exclusively referring to union between two neurons. So we will discuss few of the properties of synapses today, inshallah. The first property is the Bell-Megendie law. We will discuss what is Bell-Megendie law. Then we will discuss synaptic integration, how integration takes place within the synapses. Then we will discuss the excitatory postsynaptic potential and inhibitory postsynaptic potential. These are very important properties, EPSP and IPSP. Another property of synapse is synaptic delay, synaptic fatigue, then direct and indirect inhibition of synapse. Postsynaptic inhibition or direct inhibition of synapse, presynaptic or indirect inhibition of synapse. And then what are the effects of pH, oxygen concentration, and different drugs on synaptic transmission. Then we will discuss the electrotonic property of synapse or decremental conduction. So there are many properties of synapses. We will discuss only the properties written on the left side of your screen today. So we are going to follow the sequence given in your textbook. Rest of the properties will be covered in the coming lectures. So for today's session, we will focus on the properties of synapses written on the left hand side in red color. So you can see the other properties. We are not going into the details on these properties. We will try to focus the properties on the left hand side given in chapter 46. So the first property is Bell-Megendie law. In simple words, Bell-Megendie law states that there is unidirectional impulse transmission in synapses, and this law is applicable to the chemical synapses only. Remember, there are two types of synapses, electrical versus chemical. In chemical synapses, there is role of neurotransmitter, unlike electrical synapses in which impulse transmission takes place via fluid. So Bell-Megendie law is applicable to chemical synapses. In simple words, you can say impulse transmission is unidirectional or one-way conduction is there. That is from presynaptic terminal to the postsynaptic terminal. You can see the spinal cord cut section. Here you can see the sensory roots and the motor roots. This is the ventral portion of the spinal cord and this is the dorsal portion. And you are seeing the cut section. So as you can see, the dorsum is supplied by the sensory roots of the spinal cord. Here you can see this is the receiving end, the input, or you can say the afferent fibers. So the afferent fibers, the input or the sensory nerve fibers, they are towards the dorsal end of the spinal cord. On the other hand, the efferent nerve fibers are towards the ventral end of the spinal cord. So in simple words, Bell-Megendie law can be explained by this statement that dorsal spinal roots are sensory in nature and ventral spinal roots are motor. So you can see this is the input, the receiving end, sensory nerve roots of the spinal cord towards the dorsum, and then this is the efferent end or the motor end towards the ventral portion of the spinal cord. So the impulse transmission takes place in single direction from the receiving end towards the efferent, from the dorsal end towards the ventral end. So there is only one way conduction, that is from the presynaptic terminal to the postsynaptic terminal. This is the first property of the synapse, named after the two scientists Charles Bell and Francois Magendie, Bell-Magendie law. So this is the simplest definition of all. Bell-Magendie law states that the dorsal spinal roots are sensory and the ventral spinal roots are motor. And by this we can conclude that in chemical synapses, impulse transmission or impulse conduction is unidirectional, that is from the presynaptic terminal to a postsynaptic terminal. So this is the first property of synapse. There is one way conduction in the chemical synapse. Second property of synapse is synaptic integration, or you can say summation phenomenon. So you must have read this term in your first year MBBS classes, summation or synaptic integration. And this is the definition of summation. By summation, we mean progressive increase in the excitatory postsynaptic potential. Progressive increase in the excitatory postsynaptic potential in the postsynaptic neuron. Or you can say this is the summing up effect of the presynaptic terminal on the postsynaptic terminal. Now there is progressive increase in the excitatory postsynaptic potential. Now this progressive increase can be due to either simultaneous stimulation of the multiple presynaptic terminals or repeated stimulation of single presynaptic terminal. So we can classify summation into two types. One is the spatial summation and the other one is temporal summation or the frequency summation. Frequency summation and temporal summation both are synonymous terms. So when we use the term spatial summation, this means there is progressive increase in the EPSP due to simultaneous stimulation of multiple presynaptic terminals. Multiple presynaptic terminals, when stimulated simultaneously, this will increase the excitatory postsynaptic potential, and the phenomenon is known as spatial summation. On the other hand, in frequency summation, progressive increase in the EPSP is exhibited when a single presynaptic terminal is stimulated repeatedly, or you can say stimulated at a very high frequency. That is why we call it as frequency stimulation or frequency summation. So synaptic integration includes spatial summation as well as temporal summation. Here in this diagram you can see the two types of synaptic integration, spatial and frequency. You can see this is the postsynaptic neuron horizontally placed. This is the axon of the postsynaptic neuron. This is the soma, cell body of the postsynaptic neuron, and these are the dendrites. And you can see over the cell body or the soma, there are multiple synapses. So these are the presynaptic terminals. Presynaptic neuron 1, presynaptic neuron 2, and presynaptic neuron 3. So multiple presynaptic terminals, when stimulated simultaneously, This will create an exaggerated response in the postsynaptic neuron. And this exaggerated response produced in the postsynaptic neuron due to simultaneous stimulation of multiple presynaptic terminals is known as spatial summation. On the other hand, you can see frequency summation. In this type, you can see this is the postsynaptic neuron horizontally placed. This is the axon, this is the cell body, and these are the dendrites. This is the postsynaptic neuron. And here is the presynaptic terminal, making a synapse over the soma. So unlike spatial summation, there is single presynaptic terminal in temporal summation. You can see multiple presynaptic terminals were there in spatial summation, which were stimulated simultaneously. In temporal summation, we have a single presynaptic terminal. When this single presynaptic terminal is stimulated at a very high frequency, or you can say stimulated repeatedly, this will create an exaggerated response in the postsynaptic neuron. And this summed up effect is known as frequency summation, and or you can say temporal summation. So to summarize, if we simultaneously stimulate multiple presynaptic terminals to create an exaggerated response in the postsynaptic neuron, this is spatial summation. And if we repeatedly stimulate single presynaptic terminal to create an exaggerated response in the postsynaptic neuron, this is temporal summation. And the thing to remember is that the phenomenon of summation is exhibited by graded potentials only. And these phenomena, they are not exhibited by true action potentials. So you must know the difference between graded potential and action potential. Graded potential is non-propagated localized subthreshold response. I repeat, graded potential is non-propagated localized subthreshold response or potential, and summation phenomenon is exhibited by graded potentials only, not by true action potentials. So we have discussed two properties of synapses, Bell-Megendie law and synaptic integration or summation. The third property is the EPSP and IPSP, that is excitatory postsynaptic potential and inhibitory postsynaptic potentials. Remember, these postsynaptic potentials are graded potentials. These are not action potentials. This means these potentials, they are localized. These potentials, they do not propagate. These potentials, they do not obey all or none law. And these potentials are subthreshold potentials. So when we use the term EPSP or excitatory postsynaptic potential, this is a graded potential which is excitatory in nature. That is a depolarization response. Similarly, when we use the term IPSP, IPSP means this is a graded potential which is inhibitory in nature or hyperpolarization response. End plate potential or graded potential, they are different. The broader categories are graded potentials and action potentials. These are the two broader terminologies. Action potentials versus graded potential. Action potential can be exhibited by a nerve fiber. Action potential can be exhibited by a skeletal muscle fiber, a smooth muscle fiber, or cardiac muscle fiber. Graded potentials, the classical examples include EPSP, IPSP. End plate potentials are also graded potentials. End plate potentials are generated at the neuromuscular junction. Remember that motor end plate potential or end plate potentials, they are generated at the neuromuscular junctions. EPSP and IPSPs, they are generated not at the NMJs, they are generated at the synapses. So EPSP and IPSP both are graded potentials, number one. Both are localized, both are sub-threshold potentials, both do not obey all or none law. The excitatory postsynaptic potential is excitatory in nature, hence it is a depolarization response. Similarly, inhibitory postsynaptic potential is a hyperpolarization response. Now, depolarization can be there due to opening of sodium or potassium channels, and synaptic inhibition can be there if there is influx of chloride channels. So to summarize, EPSPs and IPSPs both are grid potentials. One is due to depolarization, the other is due to hyperpolarization. So transient depolarizations are EPSPs. These are transient for short time. So these localized potentials, they bring the membrane, resting membrane potential close to the threshold. On the other hand, the inhibitory postsynaptic potentials, they bring the resting membrane potential away from the threshold. So when you move toward the threshold, you are stimulating the fiber or the nerve. When you move away from the threshold, you are inhibiting the nerve fiber. So movement towards the threshold is depolarization. Movement away from the threshold is hyperpolarization. Depolarization is there due to influx of sodium or efflux of potassium. Similarly, hyperpolarization can be there due to influx of chloride. Remember that EPSP, IPSP, and plate potentials all are examples of graded potentials. So we have discussed three properties of synapses. We have discussed Bell-Megendie law. We have discussed synaptic integration or summation, the two types of summation, temporal summation and spatial summation. Then we have discussed excitatory postsynaptic potential and inhibitory postsynaptic potential. The next property of synapse is synaptic delay. As the name indicates, synaptic delay is the time required for impulse to be transmitted from the presynaptic terminal to the postsynaptic terminal. So the impulse, it takes few seconds, rather few milliseconds to reach the postsynaptic terminal from the presynaptic terminal. And the time consumed is due to the discharge of the neurotransmitter by the presynaptic terminal. Then this neurotransmitter will be diffused towards the synaptic cleft, or you can say towards the postsynaptic terminal. And then this will bind with the receptor site or the binding site located on the postsynaptic membrane. After attachment, this will increase the permeability of the postsynaptic membrane, hence influx of sodium ions will be there. So these events, starting from the release of neurotransmitter till the influx of sodium, all these events, they take few milliseconds, and the delay is known as synaptic delay. And the average synaptic delay is around zero point 0.5 millisecond, half a millisecond, which is almost negligible. The next property of synapse is synaptic fatigue. So when we use the term synaptic fatigue, this means there is progressive decrease in the discharge rate of the synapse. Now this progressive decrease in the discharge rate is labeled as fatigue of the synapse or synaptic fatigue, and this is a protective mechanism. So synaptic fatigue is a protective mechanism against exaggerated neuron activity, or you can say hyper excitability of neuron. And the most important mechanism which is involved in synaptic fatigue is depletion of the neurotransmitters. The most important cause is depletion of neurotransmitters from the presynaptic terminal. So when the neurotransmitters are depleted, eventually the synapse response will be fatigue. The second cause is inactivation of the receptors located on the postsynaptic terminal. Sometimes the neurotransmitters concentration is adequate enough, but the receptor sites located on the postsynaptic membrane are not functioning properly. In that case, there will be fatigue too. And the last cause is accumulation of abnormal concentration of ions in the postsynaptic terminal. So synaptic fatigue is progressive decrease in the discharge rate of synapse, and this progressive decrease in the discharge rate is most commonly due to depletion of the neurotransmitters or sometimes inactivation of the receptors on the postsynaptic membrane. So synaptic fatigue, sometimes also known as central fatigue, is another property of synapse. Now we will discuss how inhibition takes place inside a synapse, and there are different types of inhibitions. Inhibition can be presynaptic, inhibition can be postsynaptic. Postsynaptic inhibition is known as direct inhibition of synapse. Presynaptic inhibition is known as indirect inhibition. There are other types of synaptic inhibition like negative feedback inhibition, feed forward inhibition, and reciprocal inhibition. So today we are going to discuss only the pre and post synaptic inhibition of synapse. We are not going into the details of the last three types. We will discuss these three types of inhibition in the coming lectures, inshallah. So today we will focus on the post-synaptic inhibition and pre-synaptic inhibition. So when we use the term post-synaptic inhibition or direct inhibition of synapse, these are the three mechanisms involved. How synapse or synaptic transmission is inhibited at the postsynaptic neuron. The first mechanism is the opening of the chloride channels in the postsynaptic terminal. So when the chloride channels are opened up in the postsynaptic neuron, this will be followed by excessive influx of chloride ion into the postsynaptic neuron. And excessive influx of chloride ion will make the intracellular environment of the postsynaptic neuron more negative. And this negativity created will cause hyperpolarization. And hyperpolarization, once achieved, is difficult to stimulate. Hence, the synapse will be inhibited. Sometimes potassium ions are involved. So instead of chloride ions, the positively charged potassium ion channels are opened. And opening of these potassium channels will cause excessive efflux of potassium into the extracellular fluid. So in the first case, we discussed excessive chloride influx causes hyperpolarization because chloride ions are negatively charged. So movement of these negatively charged ions into the postsynaptic terminal causes hyperpolarization. In the second case, potassium channels are involved, which causes excessive efflux of potassium ions. Although the potassium ions are positively charged, but these potassium ions they exit the cells, and outward movement of potassium will create negativity inside the cell. So in that case, again hyperpolarization will be achieved. When we use the term hyperpolarization, the membrane potential is moving farther, or you can say away from the threshold. So movement of membrane potential away from the threshold will cause inhibition of the synapse, and such inhibition is known as postsynaptic inhibition. And the third mechanism of postsynaptic or direct inhibition is the activation of the receptor enzymes. And these enzymes they inhibit the metabolic functions of the synapse. Hence, the synapse activity is inhibited. So either excessive chloride influx or excessive potassium efflux. These are the causes of postsynaptic inhibition or direct inhibition. The other type of inhibition is presynaptic inhibition or indirect inhibition. So in indirect inhibition, the presynaptic terminal is affected mainly. In this figure, you can see this is the postsynaptic neuron. This one is the postsynaptic neuron, and this excitatory neuron is the presynaptic neuron. Here, I hope you can figure out. This is the presynaptic excitatory neuron, and this presynaptic excitatory neuron is making a synapse with the cell body of the postsynaptic neuron. And in presynaptic inhibition, there is contribution by a third neuron known as the inhibitory neuron. Here, you can see on top of the excitatory neuron, the third neuron, the inhibitory neuron, is involved. And the inhibitory neuron, it sends a collateral to the excitatory neuron. Here you can see the collateral. Remember, the primary stimulus for the release of neurotransmitter into the synaptic cleft is calcium influx into the presynaptic terminal. I repeat, the primary stimulus for the release of जी आप सुन सकते हैं मुझे? Okay. Sorry for the interruption. So in presynaptic inhibition, the inhibition is caused by the inhibitory neuron at the presynaptic terminal. So this inhibition causes decreased calcium influx, which is the primary stimulus. So when calcium influx is inhibited, there will be no release of neurotransmitters, and such inhibition is known as indirect inhibition or presynaptic inhibition. And this inhibitory neurotransmitter, it mainly involves the GABA neurotransmitter, or the inhibitory neurotransmitter is gamma amino butyric acid. And this inhibitory neurotransmitter will block the calcium influx at the presynaptic terminal. So synaptic inhibition can be postsynaptic, synaptic inhibition can be presynaptic. In postsynaptic inhibition, either there is influx of chloride causing hyperpolarization or efflux of potassium causing hyperpolarization. Whereas in presynaptic inhibition, there is decreased entry of calcium ions into the presynaptic terminal. Hence, there will be no release of neurotransmitter. Other things to note are that the effects of pH is there on neuronal excitability. So you must know that if the pH is greater than 7.4, this will increase the neuronal excitability, or you can say alkalosis causes neuronal hyperexcitability. Similarly, acidosis causes decrease in the neuronal excitability. So pH less than 7.4 will decrease the neuronal excitability. On the other hand, alkalosis will increase the neural excitability. Moreover, there are some drugs like caffeine, theophylline, theobromine. These are in the coffee and tea. These drugs are known to reduce the threshold, and hence it causes neuronal hyperexcitability. Similarly, strychnine is another drug, and this drug increases the threshold for the neuron, hence it suppresses the neuronal excitability. So not only the effects of pH is there, but also some drugs are also there which either increase or decrease excitability of neurons. And the last factor is the oxygen concentration in the tissues, or you can say hypoxia. So whenever there is hypoxia, this will decrease the excitability of neuron. Another property of synapse is electrotonic conduction or decremental conduction. Now, you must understand electrotonic conduction is exhibited in the dendrites commonly. You can see the neuron, this is the cell body of the neuron, and these are the dendrites. And this type of conduction, decremental conduction, this is an example of graded potential. This is not action potential, this is graded potential. Again, graded potential is a localized, non-propagated subthreshold response. So the dendrites, you can see they exhibit electrotonic conduction, or you can say they transmit impulse not by action potentials but by fluid which is located within the neuron. So these dendrites, although they cannot generate an action potential, however they can transmit impulse within the same neuron, and impulse transmission within the same neuron via fluid in the dendrites is known as electrotonic conduction or decremental conduction. Why we call it as decremental conduction? Because you can see a drop in the membrane potential as we go away from the cell body. You can see the membrane potential progressively decreases. So the farther you go from the cell body, the difficult it will be to generate an electrical potential. And these are the multiple collaterals making excitatory synapses and inhibitory synapses at the dendrites. Whether the synapse is of excitatory nature or inhibitory nature, the farther it is from the cell body, the difficult it will be for that synapse to either excite or inhibit the neuron. So electrotonic conduction is yet another property of synapse. So we discussed that the resting membrane potential of this cell body or the soma is around minus 60 or minus 65. This is the Nernst potential, named after the German scientist Nernst, who was awarded Nobel Prize in chemistry in 1920. And I hope you remember the Nernst equation from your first year MBBS class. Nernst potential is the diffusion potential across a membrane that exactly opposes the diffusion of a particular ion. And this is the equation, Nernst equation, 61 into log of concentration inside to the concentration outside. The thing to remember is that Nernst potential is the potential generated inside the cell or inside the membrane. So we will calculate the Nernst potential of these neurons. This is the neuron. Here you can see this is the cell body. This is the resting potential, minus 65 millivolts. And here you can see the distribution of different cations and anions, sodium, potassium, and chloride ions. Concentration of sodium is greater outside than inside. Concentration of potassium is greater inside than outside. Similarly, concentration of chloride is greater outside than inside. So a gradient is there known as concentration gradient. So the concentration gradient for sodium ion will drive the sodium ion to move into the cell. Similarly, the concentration gradient for potassium ion will drive these ions out of the cell. On the other hand, the concentration gradient will tend to drive the chloride ions into the cell. So this is one of the gradients, that is concentration gradient. And the other gradient is known as electrical gradient. So when the sodium ions they move downhill, down the gradient into the cell, this will cause increased negativity outside the cell and increased positivity inside the cell. Similarly, when the potassium ions they move downhill or down the gradient out of the cell, so outward movement of potassium ions will make the inside more negative. Now this negative electrical charge will attract potassium ions back to the cell. So this is the electrical gradient. So what is Nernst potential? The potential at which the concentration gradient and the electrical gradient is neutralized. So both these gradients are neutralized and there is no net movement of the ions. So the Nernst potential for the sodium ion is plus 61 millivolt. We have applied the formula log of concentration inside to concentration outside. Similarly, the Nernst potential for potassium is minus 86 log of concentration inside to log of concentration outside. And then the electromotive force, or you can say the Nernst equation for chloride is minus 70. And this negative or positive charge, it all depends on the potential generated inside the cell. For example, sodium ions are positively charged ions. So influx of sodium will cause positivity inside the cell, hence the nonce potential is positive. Efflux of potassium will cause negativity inside the cell, hence the charge is negative for potassium. So here you can see the resting membrane potential is around minus 65. Mind you, this RMP of minus 65 is different from that minus
सर
90 millivolt RMP of peripheral nerve.
सर टाइम हो गया लेक्चर का.
Okay, last slide, last slide. So the RMP is around minus 65. This is the resting potential. Inward movement of sodium ions will make this resting potential less negative. Hence, the neuron is said to be excited. Similarly, inward movement of chloride ions will make the resting potential more negative. Hence, the neuron is said to be inhibited. So, either chloride influx or potassium efflux. In either case, there is excessive negativity inside the cell. So, this is hyperpolarization for you, right? So today we have discussed properties of synapses. We have discussed Bell-Megendi law. We have discussed synaptic integration. We have discussed synaptic delay, synaptic fatigue, EPSP, IPSP. All these are important properties of synapses. Thank you very much.